For more than 100 years, there's been this one rule in physics that felt totally absolute. Nothing with mass can travel at the speed of light, and definitely not faster. But what if that rule was never the whole story? What if the universe has had a secret fast lane this whole time? And that's exactly what we're digging into. A team of physicists from the University of Warsaw and the University of Oxford just published this incredible paper. In one of the world's top physics journals. They took an idea that's been dismissed for decades as just, a mathematical fantasy, and showed how it could be a real, consistent part of our universe. And right there, that's the price of admission for this whole new way of thinking. It's this completely mind-bending idea that turns our whole concept of cause and effect on its head. In this new picture, the destination can actually shape the journey. So how on earth did we get here? Well, to understand this huge leap, we thought to go back to the rule it seems to break.
Right, so we all learned about the cosmic speed limit in school, but it turns out the way we usually learn it, it's just not the complete picture.
This is the foundation, right? Back in 1905, Einstein showed that the speed of light in a vacuum is the same for absolutely everyone, no matter how fast they're moving. And from that one simple fact, this hard limit just pops out. For anything that starts slower than light, like you and me and this planet, reaching light speed would take an infinite amount of energy. It's like a wall you can get closer and closer to, but you can never, ever touch it.
But here's the thing about that universal rule. It's got some serious fine print. See, Einstein's equations totally lock the door on anything trying to go from slow to fast. But what if something was just born on the other side of that wall from the very beginning? And that's the loophole. It turns out the mathematics of relativity doesn't actually forbid faster than light travel at all. In fact, it explicitly allows for 3 completely different classes of particles, and it all depends on their relationship to the speed of light.
Okay, this is where it gets really fascinating. The math doesn't just give us one speed limit. It suggests 3 different lanes on the cosmic highway. For us and all the matter we know, which physicists call bradyons, the speed of light is a ceiling we can never break through. Then you've got massless particles like photons, the Luxons. For them, the speed of light is the only speed they can travel. But now look at this third class, Tachyons. For them, the speed of light isn't a ceiling, it's a floor. They are born faster than light and can never slow down enough to reach it.
So you're probably asking, okay, if the math has allowed for this all along, why isn't this in every physics textbook? Well, because for more than 50 years, the whole idea was seen as a complete disaster waiting to happen. Mathematically possible, sure, but physically catastrophic. There were these 3 specific, really, really bad problems that just made the idea toxic. First, a tachyon field would make the vacuum of space unstable, meaning empty space could literally just disintegrate into a shower of particles. Not good. Second, 2 people moving at different speeds would actually disagree on whether a tachyon even existed. That completely breaks the rules of physics. And third, they could have negative energy, which would violate the fundamental laws of thermodynamics. These weren't just little problems, they were absolute theory-killing deal breakers. But then this 2024 paper comes along. And what these researchers showed was that all 3 of those so-called fatal flaws, well, they weren't actually flaws in the idea of tachyons at all. They were flaws in the math we were using to describe them. Think of it like this. Imagine physicists were trying to map the entire Earth, but their atlas only showed the northern hemisphere. Of course, the global picture wouldn't make any sense. The standard framework they were using, this thing called quantum field theory, which is our best description of reality, was just too small. It couldn't fit faster than light particles without creating all these weird contradictions. So the solution then was actually beautiful in its simplicity. You just complete the map. The team extended the mathematical framework to include not just things moving forward in time, but backward as well. And in this bigger, more complete picture, all 3 of those fatal flaws, the unstable vacuum, the observer disagreement, the negative energy, they just vanish. So, okay, the math works now. The theory is clean. But this leads to the biggest question of all. Is this just a really clever piece of math? Or is nature actually using it? And this is where the physics community is right now, standing at this huge fork in the road. On one side, you've got theory A, the conservative view. Sure, the math is beautiful, but we've looked for tachyons and found nothing, so it's probably just a neat idea. But then there's theory B, the really radical alternative. No, this math is telling us something incredibly deep about the universe, and it's time to start looking for the new things it predicts.
And that's the key here. This isn't just philosophy. If theory B is right, it makes specific predictions we can actually go out and test. It suggests a new kind of quantum entanglement, that spooky action at a distance, but acting across time instead of space. It predicts we might see weird new signals in our most powerful particle accelerators, or maybe even find these faint echoes of a faster-than-light era hidden in the cosmic microwave background, which is the oldest light in the entire universe.
And that last point, the echoes from the beginning of the universe, that leads to the most stunning implication of this entire paper. It suggests that tachyons weren't just some weird possibility. They were essential for our universe to even exist in the first place. So what the paper proposes is that for the first trillionth of a second after the Big Bang, the universe was in this tachyonic era. The Higgs field itself, the very thing that gives all other particles their mass, was behaving tachyonically. Its ripples were moving faster than light. Then, as the universe cooled, a phase transition happened. The tachyons basically condensed into the slower-than-light reality we live in now, and the arrow of time as we know it emerged from that single moment. And this isn't some distant, abstract idea. The theory implies that the very stuff you're made of, the atoms in your body, are the settled leftovers of that initial superluminal state. Our slow, orderly world was born from a faster-than-light chaos. Which leaves us with this final, truly profound question. If this theory is correct, and if the future really can influence the present, what does that mean for causality, for free will? Is the universe a story that's being written one word at a time from beginning to end? Or is it more like a pattern that's being completed from both ends at once? For the first time, that's not just a question for philosophers. It's now a question for physicists. And the answer? Well, it could change everything.